Have you ever stopped to think how the simple motion of wind turning a turbine or water rushing through a dam can somehow power an entire city? It kind of seems like magic, right? But it's pure, unadulterated physics. Today, we're going to pull back the curtain on the brilliant principles that connect motion, magnetism, and the electricity that runs our entire world.
So, at the very heart of it all is this one question. How does it really work? It's not just about turning a crank. It's about a deep, fundamental dance between the forces of nature. And stick with me, because by the end of this, you'll understand exactly how it's done.
All right, so our story begins with a monumental discovery, one that literally lit up the world. We're talking about the moment we figured out that magnetism could actually create a spark.
Now the key word here, the absolute game changer, is changing. A magnet just sitting next to a wire does, well, absolutely nothing. Zilch. But the second you move that magnet, the second you change the field, bam, an electric current just appears out of thin air in that wire. This is electromagnetic induction, a discovery by the great Michael Faraday, and it is the foundation for pretty much all the electricity we use.
So, to really get a handle on this change, we need to talk about something called magnetic flux. Okay, don't let the name scare you. You can just think of it as the total amount of magnetism flowing through a specific area, like a loop of wire. The more magnetic field lines you can cram through that loop, the higher the flux.
And this picture shows it perfectly. This flux thing really just depends on three things. How strong is your magnet? That's B. How big is your loop of wire? That's A. And what's the angle? Are you holding the loop face on to the magnet or sideways? Change any one of those, the field strength, the area, or that angle, and you've changed the flux. And as we just found out, changing the flux is exactly where the magic happens.
And that brings us right to Faraday's law. Now, don't get hung up on the fancy math here. That d phi by dt part is just physicists speak for how fast the magnetic flux is changing. That's it. So the law is just saying the induced voltage you get is all about how fast you change that flux. The faster you move the magnet, the more voltage you get. But hang on. Look closely at that formula. You see that tiny little minus sign? It might look small, but trust me, it holds a deep secret about how the universe works. Yeah, that minus sign is our gateway. It leads us straight to the main event, Lenz's law. And Lenz's law is all about nature's fundamental tendency to fight back. Seriously, that minus sign basically is Lenz's law. While Faraday's law tells us how much voltage we're going to get, Lenz's law tells us the direction, which way the current is actually going to flow. And the rule is simple. The current will always flow in a direction that opposes the very change that created it in the first place.
And here it is, the official definition from Heinrich Lenz himself. The system just wants to keep things stable. It loves the status quo. So if you try to increase the flux, it's going to fight to push it back down. If you try to decrease it, it'll fight to pull it back up. It's basically nature crossing its arms and saying, nope, you're not changing things around here without a fight.
Okay, let's see this in action, because this is cool. We've got the north pole of a magnet, and we're moving it toward a coil of wire. As it gets closer, more and more magnetic field lines are going through that coil, so the magnetic flux is increasing. Now, according to Lenz's law, that coil is not just going to sit there and let that happen.
And here's the fight back. To oppose that incoming north pole, the coil instantly induces a current that turns itself into an electromagnet, with its own north pole facing the magnet. And we all know what happens when you put two north poles together. They repel. They push away from each other. That repulsion is the opposition. And in order to create that very specific magnetic pole, the current had to flow in a specific direction. Just like that, Lenz's law told us which way the electricity is going to flow. So why all this opposition? Is nature just trying to be difficult? Not at all. It's tied to the most fundamental rule in the entire universe, the conservation of energy. You can't get something for nothing. I mean, just imagine if the coil helped you, if it attracted the magnet instead. It would just get sucked in, speeding up, creating current for free. That would be a perpetual motion machine, free energy. Lenz's law is what prevents that. It guarantees that you have to do work. You have to physically push against that repulsive force, and the energy you spend pushing is what gets converted into electrical energy.
Okay, now that we understand this whole principle of opposition, let's see how we've cleverly used it to build our entire civilization. It's time to talk about the generator.
So, what is a generator? It's really just a machine that's designed to do exactly what we've been talking about. It's a converter. You feed it mechanical energy, like something spinning, and it uses electromagnetic induction to transform it into the electrical energy that powers our lives.
And a basic generator is beautifully simple. You've got a magnetic field, usually from some powerful magnets. You've got a coil of wires sitting right inside that field, and then you just need a way to mechanically make that coil spin. That's it. Those are all the essential parts. So the process is really elegant. You start turning the coil. As it rotates, that angle between the coil and the magnetic field is always changing, which means the magnetic flux is constantly changing. Faraday's law sees this and says, hey, we've got changing flux. Let's induce some voltage. Then Lenz's law chimes in, making sure the current creates a magnetic force that actually fights against the rotation. That's why you have to put in effort to turn it. And finally, that current flows out to power whatever you've hooked up.
Now, there's a really crucial distinction to make here: AC versus DC generators. You see, as that coil spins, the current naturally wants to flow one way for a half turn and then the other way for the next half. That's alternating current, or AC. An AC generator just lets that happen using simple connectors called slip rings. But if you want direct current, or DC, where the electricity flows in only one direction, you need a clever little invention called a split ring commutator. It's basically a switch that flips the connection every half rotation so the output always flows the same way.
So you see, this one principle, this dance between Faraday's and Lenz's laws, isn't just some neat little physics experiment. It is, without a doubt, the engine of our entire modern world.
Just think about it for a second. In a hydroelectric dam, falling water is what provides the mechanical energy to turn the generator's coil. In a power plant, it's steam from burning fuel that turns the coil. In a wind farm, the wind turns it. The source of the spin changes, but the fundamental physics happening inside that generator is always the same.
Let's just put some quick numbers on this. Imagine the magnetic flux in a coil drops from 0.8 units down to 0.2, and that change happens in just 0.2 seconds. The total change is negative 0.6. But Faraday's law has that little minus sign, right? So a negative of a negative gives us positive 0.6. You divide that by the time, 0.2 seconds, and you get an induced voltage of 3 volts. It's a direct calculation.
Which brings us to one last fascinating question. If a generator creates electricity from motion and an electric motor creates motion from electricity, why can't we just hook them up together and create a machine that powers itself forever? The answer, as we've seen, is our good old friend Lenz's law, that constant opposition. The generator will always create a magnetic drag that fights the motion driving it, which means you always have to put more energy in than you get out. There's no free lunch in physics. But thanks to these laws, we do have the power to light up